Hi, this is Aki Fujimura from D2S, the managing company sponsor of the eBeam initiative. Today, I'd like to talk to you about mask hotspots and the increasing importance of mask hotspots and making sure that no mask hotspot escapes your mask shop in the future. Mask hotspots are hotspots or problems that show itself in wafer yield or chip performance by having the mask shape on the mask not be the same as what was designed on the mask by OPC. Litho hotspots, everybody knows, or OPC hotspots or litho hotspots, everybody knows is the majority of the reason why wafers or chip performance fail. But increasingly, mask hotspots are becoming the issue, and the eBeam Initiative survey from 2013 showed that the industry luminaries surveyed believe that mask hotspots are going to be very significant by 2020. 75% of the people interviewed thought that, and 50% of the people thought that mask hotspots would be about as bad as litho hotspots, which means what was only 5 years ago kind of a non-significant issue, mask hotspots wasn't really that prevalent back then, is going to become a very, very important issue. This is a huge change in the industry, and I think one of the issues that is going to contribute to that is the importance of mask resiliency to mask manufacturing variation. So I'd like to go through the kind of the technical details of that today. In talking about mask hotspots, I want to talk about the conventional fracturing flow first. So if you don't use model-based MDP approach, then in conventional fracturing today, the processing from the CAD point of view is all geometric, or they are rule-based. There's some verification that goes on in an XOR check, the differences, geometric differences kind of a check, but there's no simulation in the flow. Mask writing happens, mask processing happens, inspection and repair and SEM and so on happens down the line, but mask inspection cannot see because it's looking at it with light. It's magnified, but it's still looking at it with light. So mask inspection at best can tell 2D features of 20, 30, 40 nanometers is all it can see. So throughout the whole flow, either in simulation or in inspection, there is nothing that is checking to see 2D feature differences of the mask shape to the desired mask shape before it goes out of the mask shop. So in this way, feature differences of significant deviation are escaping the mask shop today. So now let me talk about the types of problems that escape the mask shop. Looking at this picture here, these are simulation pictures of what might happen on a mask. There are nominal contours that are simulated with these red circles from the pictures of shapes that were described by OPC. Now, of course, all of these corner roundings and things are anticipated by OPC, but they're not simulation-based anticipation, so you don't really know exactly what the mask shape is going to look like when the mask is produced. The variation in contours, this is one possible contour. This one looks maybe too small, but acceptable. But this contour on the outside, where there is this pink bridging area, this is not acceptable. The difference between the inner contour and the outer contour is all about those variation, or manufacturing variation that is proxied by analysis based on those variation. So higher dose might cause these shapes to bridge together when they're not supposed to be bridged together. Lower dose, it's going to be too small maybe, but at least they're not bridged together. The opposite effect is on this picture, where the CAD shape that OPC output is this rectangular shape. Sometimes, when the dose is adequate or dose is high enough, it has a contour. Even then, it's not reaching the top, which is a subject of a different discussion. But sometimes it's so low that it's not even half of the distance of the whole thing, and that's a problem. So this, in this case, lower dose is causing the problem. In this case, higher dose is causing the problem. So these reflect the analysis, kind of simulation-based analysis that must be done in order to find out if you're going to have a mask hotspot in reality. The important part of it is that mask hotspots require simulation-based analysis of the full chip and require dose margin-based analysis for manufacturing variation. So I talked about the conventional fracturing flow, where today these mask hotspots are escaping the mask shop. In the model-based mask data preparation MB-MDP flow, they do not, because at the simulation spot, here, everything, the full chip is being simulated inherently as a part of MB-MDP processing. So because of that, included in this mask data preparation flow are things like linearity correction, or sometimes talked about as MPC, or dose margin correction, or enhancement, like sometimes people call it MPE, mask process enhancement, and also model-based mask verification, a full chip model-based mask verification. It's a simulation-based check, both for nominal contours and for dose margin check. In that flow, even though when you get down to inspection, it's still true that they can only see 20, 40 nanometer, really, 20 nanometer to 40 nanometer 2D differences, because you are checking at the simulation stage at the full chip level. Every contour, every spot on the contour on the full chip can be verified so that mistakes don't escape the mask shop. So MB-MDP approach is correct by construction in addressing these kinds of mask hotspots. But what about conventional fracturing flows where mask hotspots are escaping the mask shop today? In conventional fracturing, there is no simulation, so clearly the way to address this issue is to add a full chip simulation step to the flow. And that would be our proposal, a model-based mask verification step that is a no-risk insertion. It's not really correcting anything automatically at this stage, so there's no risk, right? And you want to be able to insert this step in such a way that it does not add to the mask shop's turnaround time. Now, this is, of course, every mask shop's choice, and it's probably a choice that every mask shop can make on a per mask basis, but depending on the risk profile, right? But mask writer can be writing the mask simultaneous with the model-based mask verification step. And when you do that, you are able to insert this check, full chip simulation check, without affecting the turnaround time. Now, some people might say, if something is wrong, we don't want to have the writer's time wasted. Well, in many of the cases, these types of issues can be corrected in the repair step, and that's what would be done anyway, and in that case, there's no time wasted. And in some cases, where maybe the mask writer's time was wasted, you have to do it again. Well, in that situation, if you don't do model-based mask verification, you would have found out about that after the mask had gone to the wafer shop. So this is much better anyway. But in any case, this is the individual choice of every mask shop for every mask that you can make. You can either insert it in place of verification or in addition to XOR-based verification, or you can have it in parallel to mask writing. Model-based mask verification we propose is something that is absolutely essential to all of the critical layer masks in the upcoming technology nodes. Why? Because mask hotspots will be escaping the mask shop if you don't do that. There is nothing else that checks at the full chip scale what might be wrong in nominal conditions or in manufacturing variation conditions as checked by those margin checks.